Welcome back. Now we're looking at a problem about a campus coffee house. The campus coffee house wants to determine if the average amount of money students spend per visit differs from the national average for campus coffee shops. The national average amount spent per visit is $7.50, with a known standard deviation of $1.20. The coffee house randomly samples 30 transactions from students and records the amount spent per visit. At a 0.05 or 5% level of significance, they want to test if their average amount spent per visit is different from the national average. Okay, so here's the sample, and we're going to first set up our comparison. So we're looking for X bar, which is the sample mean for this particular sample that was taken from campus coffee. So that equals average. Oops. And so their average from that sample is 770. The problem says that the national average is 750. And so what we're trying to decide in this problem is it reasonable, right, that you would get a sample of 770 if the national average was 750? In other words, would that difference just be sampling error, or is that a real difference? All right, so let's keep going. So the sample size is a count of all these numbers. 30. And we're looking at the standard deviation, which is called sigma, for the population. And that was given in the problem as $1.20. So 1.20. Alpha was given in the problem as 5%. Okay, now we come over here. The expected variability is given by, for z-test, is given by that's called the standard error, or you could also think of it as sampling error, is sigma x bar, the standard deviation of the x bars, which is equal to the regular standard deviation divided by the square root of n. So that's the one we'll pick. What we're dealing with in this distribution are x bars, not x's, because these are all samples. So that's why it's full of x bars, just like each of the x bars in the cookie problem was an average of the size of the 4 cookies. It's a z-score, and we're looking for the probability of x bar, since that's what's in here. What's the probability of these x bars where the sample size is 30? So the distribution is a normal distribution. The comparison value is the critical value of x bar, because we're setting up here basically the boundaries here, and then our test stat is down here. So here's the critical values, here's the test stat. It's going to be a two-tailed test, so we'll have a left and a right. So there's the left. We always start with the left and then do the right if we have both. And the hypothesized mean was given in the problem. That's this one here, so it equals that. The expected variability, we start out with the standard deviation, which is given in the problem, and divide it by the square root of the sample size. Then the x bar, now we're trying to figure out, we realize that's too big a tail. So we're trying to figure out just how small it is, and getting these next 3 numbers will get us there. But because of the arrows, we have to start here with a probability. So it starts out equal to, alpha divided by 2, because it's going to be a two-tailed test. And we also know that we're working up here, probability of x bar to x bar. So we've already done the standard error. And now we're looking at the left-hand side. So the z-score will be norm.s.inverse of the probability of x bar, which was this one. So it equals norm.s.inverse of this guy. Now the tail's smaller, and because the tail is built off of the z-score. And then to get x bar, we take that z-score, multiply it by the standard error, which basically means that's how many or how z-scores we have, and then add it to the mean. I get 707. So that's the raw value here. And then we have to do the other tail. So this becomes the right tail. This is the same, and so is this. These will always be the same all the way down. But these last three will change. All right, so we start out by the probability is equal to that divided by 2. Now, this is the right tail, so we use this one with the arrow pointing right, norm.s.inverse, not 1 minus probability of x. So equals norm.s.inverse 1 minus this probability. And then it's going to be the same equation for the for this guy. It's going to be the z-score times the standard error plus the original mean. Basically, we're trying to see how far away we are from the original mean. In other words, starting at this point, how far are we this way or this way? And so that one ends up being 7.93. So that's this guy here, because it's the right-hand one. All right, and now we get to work with the test stat. So same distribution. Now we have to figure out where we are. Well, we actually know where we are because the mean, hypothesized mean is 750 and we're at 770, so we're to the right. So the shading should be right. It's obviously not quite that big, so we'll figure out exactly what it is. So first we can copy the mean. Expected variability, that's the same also. And now we actually work this way. We've got the raw sample mean, which is this number. And now we are going from x bar to p of x bar. So the z-score, you can see it there, is x bar minus mu divided by sigma x bar, which is also the standard error. So x bar minus mu divided by the standard error. So that's going to be x bar, which is the sample mean, minus mu, which is the population mean, divided by the standard error. And then we need the probability of x bar to the right, so it's going to be this one here, 1 minus norm.s.dist equals 1 minus norm.dist of that z-score, and then it's true. So 17.7. All right, now note that, and this doesn't happen much in our problems, because usually we give you a problem where the result is significant, but this one is not. You'll notice that this gray line is not starting in the pink area. In fact, it's outside of, and that means that this result is not significant. This is not an unexpected difference, which means that we are going to, in this case, fail to reject the null hypothesis. In other words, we're saying, hey, that difference is not that big. That's actually sampling error. But we'll flesh this out so that you can see it. So first, the null hypothesis is no real change. The population mean for campus is 7.5. We observed a sample mean X bar of 7.7 just because of sampling error. So that's how you say that. The two are the same. Or there is a real change. The population mean for campus is different from 7.5. There is a true difference in means. And the standard error is the sampling error and measures the expected variability. And we said that was going to be calculated by the standard deviation divided by the square root of the sample size. The test statistic is a z-score. And the critical value, right, what we're asking is, where is this test statistic in relation to the two critical values here? And it's actually between them. So we need to say that. It's between the critical values. And that means that it's not statistically significant. And also, as far as probability goes, the probability of this value is 17.7%, which is more than the 2.5% in this tail. So we need to say that too. The probability of X bar is actually greater than alpha in that tail. And so, in this case, we fail to reject. The reason we fail to reject is because this is not true, right? The test in the p-value do not indicate significance. In fact, they indicate just the opposite. So if we reject the null, we accept the alternative, and we should indicate the direction of the difference, but we're not rejecting the null. So we're really saying the two are equal. Which is wild, right? Because you're thinking, well, that is a difference, but not a meaningful difference. That could have just been sampling error. Approximately what raw value is the lower cutoff for a statistically significant sample mean X bar? And that's going to be the 7.06 down there. Approximately what raw value is the upper cutoff? That's 7.94. How much probability is in the fail to reject range? 95%. And we fell into that 95%, which is why we did not reject the null. What's the size of one standard error in this problem? You get that there. That's the 0.22, right? Because as you go from 0 to 1, that's one standard error, so that's 0.22. And what's the raw value at 0.93 standard errors? And there it is, 0.93 standard errors. The raw value is the 770. So are we statistically significant? No, we are not. And we're done with this one. We'll see you in the next video.